as opposed to the average velocity or speed, which is averaged between two distinct points in time. Sorry, give me 1 second here. All right, so instantaneous velocity and speed is the velocity and speed occurring at a single instant in time. If we had a trip from point A to point B, and an object were to travel along some path during this trip, we can measure a distance d along the path, right? That's how far you actually travel along the path. And from that distance, we can measure the average speed as being the distance along the path divided by the amount of time it takes to go from A to B. Or we could define the displacement from A to B, the displacement being independent of the path, and we can define the average velocity from A to B as being the displacement from A to B divided by the amount of time it takes to get from A to B. Neither of these numbers are guaranteed to be close to the instantaneous velocity or speed at any particular point along the path. If you want to know the velocity or the speed at this instant, what is the velocity or the speed at this instant? There's no guarantee that the answer to that question is going to resemble either of these numbers. And the reason is that the window over which you're measuring the velocity and the speed is just too large. Okay, imagine driving in your car, that if you're going from point A to point B, and that's 15 miles, and it takes you half an hour, you're going to average 30 miles an hour. But what if at this instant, you're on an expressway and you're going 70 miles an hour? Or what if at that instant, you're at a red light and you're going 0 miles an hour? There's no guarantee that your velocity or speed at that instant is going to resemble your averages. So what you do is, instead of measuring the velocity and speed over the whole trip from A to B, you shrink that window down to a very, 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 very tiny window. So you say, instead of measuring it from A to B, I'm going to measure it over a very, 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 very small window. Okay? Measure over a very small time window. Okay? That very, very, very tiny time window will give us a much more accurate measurement of what the velocity or speed is at a particular instant. Because if you make the window small enough, you do not give the car, or the object in general, you don't give it enough time to change its velocity or its speed. Okay? That if you want to know at the instant of 1 p.m. what your velocity is at this instant, what's the velocity or speed at this instant, measuring it from noon to 2 p.m., that 2-hour window is really, really, really big, and you're not going to get a number that closely resembles your velocity or speed at 1 p.m. But if you measure it from 1 p.m. minus 1 nanosecond to 1 p.m. plus 1 nanosecond, that 2 nanosecond time window is not enough time to allow your car to change its speed. Your car will not be able to change its speed at all in 2 nanoseconds. That's 2 billionths of a second. Yeah.
So this resembles the delta t, right?
That's the value of delta t. This is the size of delta t.
Yeah, so
we're specifically choosing a very small delta t.
So technically it wouldn't make a difference if you would basically divide the distance by 1 nanosecond, for example, right? It would give us the
Yes,
same
you would have to figure out how far it traveled in the 1 nanosecond. But if you could measure how far it traveled in 1 nanosecond, which would also be very small, and you divided that by the 1 nanosecond, that would give you a very, very accurate measurement of the speed at that instant.
So like for example, let's say a car travels around from like it goes from 8 a.m. to like 12 p.m. for example.
Yeah.
No, let's say 2 p.m. This 1 nanosecond, let's say we would measure at 9 a.m.
Yeah.
and let's say as we said 1 p.m.
Yeah.
This 1 nanosecond would be the same for both, so the speed would be
No, because the distance that you would travel during those 2 nanoseconds would be different.
Oh.
It's a measurement that you'd have to continuously make.
Yeah.
So the averages are measurements that you only make once at the end of your trip. Once you've gone from A to B, you measure either the distance traveled or the displacement traveled divided by the total trip time, and that's your one measurement. But let's say that you were on a trip that went from 12 p.m. to 5 p.m. and you wanted to know your instantaneous speed or velocity at multiple times. Every time you wanted to know it, you'd have to make a new measurement. What's your speed at 12:05 p.m.? You would measure it from 12:05 plus 1 nanosecond and 12:05 minus 1 nanosecond, and that would be your delta t around 12:05. Figure out what your distance and displacement was during that delta t, divide it by 2 nanoseconds, and that's your speed and velocity at that instant. At a future time, let's say 3:12 p.m., measure 3:12 plus 1 nanosecond, 3:12 minus 1 nanosecond, and there's your window for that new measurement at 3:12. So the instantaneous value is something that you have to keep measuring. Okay? If you're in a car, the speedometer gives you the instantaneous speed that you're traveling at, and that speedometer is continuously updating as your trip goes on. Okay? So if you hit the accelerator and you allow some time to change, that speedometer reading is going to rise because you're gaining speed. So your instantaneous speed is increasing. You hit the brake and allow some time to change, the speedometer reading will drop because you're losing speed. So instantaneous values have to be continuously updated throughout the trip, whereas averages are only measured once at the end of the trip. Okay? Any other questions? Another feature of the instantaneous velocities and speeds that's dramatically different than the averages is we had an inequality for the averages. Over the entire trip from A to B. For instance, this trip that I drew here. We know that the distance has to have what relationship to the magnitude of displacement? The distance along the path taken has what relationship?
greater or equal to?
Greater than or equal, right? The shortest path between any 2 points is a straight line. So if you take a curve that's not straight, your distance has to be greater than the displacement. So your distance will always be greater than or equal to this. Since that's true, if you compare the average speed to the magnitude of the average velocity, the average speed will always be greater than or equal to the magnitude of the average velocity. Okay?
Sorry, sorry, you said if it's a straight line, you would be.
then it's an equal sign, if it's a straight line. So if the path is not curved from A to B, but the path is just straight from A to B, then those will be equalities. Those would be equal signs, not greater than. Okay? Any other questions? Remember that the displacement is always this vector from A to B because the displacement has nothing to do with the path taken. The distance does have to do with the path taken. All right? But now imagine that we're trying to measure the distance and the displacement over a very, 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 very tiny time. We're only allowing this really, really, really small amount of time to pass. So think about the path that your car would have to travel over an incredibly short amount of time. If in general, this was the path taken over some large amount of time, this is A, this is B. If we zoom in really, 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 really close to a particular segment of the path, and we only allow a very small amount of time, then the path taken over this very short amount of time is always going to be straight. The path taken over this very short amount of time will always be straight.
What do you mean?
I'm going to explain that in a second. The path taken over a very small time will always be straight. Okay? There are a couple of different ways that you can see this. Think about being in a car and think about trying to measure it over these 2 nanoseconds. Is that enough time for your car to speed up or slow down significantly?
No.
No, right? This is such a small amount of time that your car cannot change its speed, so that's why that's a good measurement of the instantaneous velocity. Because the speed or the velocity that you're traveling at here is the same that you're traveling at here, and it's the same at 1 p.m. But likewise, is that 2 nanoseconds enough time for your car to turn significantly?
No.
No. If you even thought in your head, I want to turn my car, the electric signals from your brain to your arms would be slower than 2 nanoseconds. If you turn the wheel, the instant that your car tried to start turning, those 2 nanoseconds would be over. 2 nanoseconds is not enough time to turn your car whatsoever. Okay? It's much, much, much too little time for a curve to develop. Okay? Your path is always going to be a straight path if you consider a time that's short enough. Okay? There's also a natural phenomenon called local flatness, which tells you that any curve, if you zoom into that curve far enough, that curve will always appear straight. We see this every day on the surface of the Earth. The Earth is not flat, the Earth is curved, but it appears to be flat because we only see short distances along the surface of the Earth relative to the radius of the Earth. Okay? The Earth has a radius of like 6.5 million meters, but we only see distances of hundreds or maybe thousands of meters. Okay? So the radius of the Earth is like 10,000 times larger than any distance we measure. So it appears to be flat because it's like we're zoomed in really, really, really far on that curve. Okay? If I were to try to zoom in on a piece of this curve right here, it might look slightly less curved. If I zoom in on a piece of it right here, it's going to look less curved. And the more that I zoom in, the more that curve appears to flatten out. Okay? It's a phenomenon called local flatness. It's just a feature of math. Okay? Any curve, if you zoom in very, very, very close to that curve, if you only consider a tiny piece of it, it will always appear straight. Yeah.
Basically like finding a tangent, right?
Yeah.
Finding a tangent of the line.
Yeah.
Like we have a constant.
Yeah. Okay? And that's the business of calculus. That I've been avoiding talking about calculus specifically, but this is all stuff that you would do in calculus. We're not going to actually use the tools from calculus, since this is a physics without calculus class, but you can still understand the idea of it without actually using the tools you would learn in calculus. Okay? Now, because the path is always straight, what does that mean about this equality?
Equal.
They're always going to be equal. Okay? So the instantaneous speed is always equal to the magnitude of the instantaneous velocity. Because over a very, very, very short time, the path will always be straight. Okay, the instantaneous speed will always be equal to the magnitude of the instantaneous velocity, because over a very small time, paths are always straight. We denote the averages by putting this little AV, sometimes as an AVG, as a subscript. To denote instantaneous values, we just don't put the average symbol below it. So we would just say that V equals the magnitude of the vector V. Okay, it's important to understand this key difference between average and instantaneous values. That the instantaneous speed is always the magnitude of the instantaneous velocity, but the average speed is not necessarily the magnitude of the average velocity. Okay? Any questions? All right. Now, the last kinematic variable that we're going to talk about is acceleration. And acceleration has the same relationship to velocity that velocity has to position. So velocity roughly measures how quickly you're changing your position over time. That if I tell you your velocity is 5 meters every second, you're gaining 5 meters of position every second. Okay? Acceleration tells you how quickly your velocity is changing with time. Okay? So if I tell you your acceleration is 5 meters per second, then you're gaining 5 meters per second of velocity every second. Okay? Acceleration is the rate of change in velocity over time. Okay? Acceleration is typically given by the letter A. Acceleration is a vector because it's a change in velocity, and velocity is a vector. The units of acceleration, remember that this notation, these square brackets, are the units of A. this is going to be meters per second, but typically people don't write it like this. Typically they write it with the second, both of them in the denominator, and you just make it squared. So it's meters per second squared. That's the more common unit. Okay? A velocity of 5 meters per second means you're gaining 5 meters of position every second. You're increasing your position by 5 meters every second. An acceleration of 5 meters per second means you're gaining 5 meters per second of velocity every second. Okay? Let's talk about a few properties of acceleration. First of all, there's an instantaneous versus an average definition for acceleration. So the average acceleration is going to be defined just by the definition. It's a change in velocity over time. So if you're traveling on some path from A to B, right, here's your trip, and at A, you're moving with some velocity v at A, and at B, you're moving with some velocity v at B, then there's going to be a change in velocity over your trip. Delta V is the final velocity v at B minus the initial velocity v at A. If that trip takes a time delta t, then the average acceleration is just the amount that your velocity changed over the trip divided by the time the trip took. Okay? How do you guys think that you would measure an instantaneous acceleration? If I wanted to measure
The velocity before and after a certain distance.
but this is from A to B is already a velocity before and after. Why can't I just use those velocities?
Depending on how, like probably a second or a second, because it's over meters over second squared, so you need it probably for seconds.
Because it's
No.
not constant.
Yeah, the acceleration is not necessarily constant. So how can I change my approach? I want to take the same approach that I took measuring instantaneous velocity. What did I do? Instead of measuring it over the whole trip, what did I do to get a good value of the
The second,
instantaneous?
the second, one before, one after.
You just made it, the window really, really, really small. So instead of measuring it over the full time it takes to go from A to B, you're measuring it over a very small time. So the instantaneous acceleration is going to be the same thing. You just have to make sure that delta t is very, very small. Okay? To measure instantaneous, I'm just writing as INST dot to save time. To measure instantaneous acceleration, you must use a very small delta t. But it's the same basic definition. Okay? Now, the good news is that in this class, for the vast majority of applications, we're going to be dealing with accelerations that are constant. For any value that does not change with time, any value that's constant in time, the average and the instantaneous are always the same. Okay?
What's after must? You must what?
You must use a very small delta t. So imagine this trip from noon to 5. What if I told you that over the entire trip, your speed was constant? And it was 30 miles per hour, constant during the entire trip. How fast would you be traveling at noon? 30. How fast would you be traveling at 12:05?
30,
How fast are you traveling at 3:12?
30,
How fast are you traveling at 5?
30.
30. If the number is constant and it doesn't change, then the average and the instantaneous are always the same. Those numbers are only different if the value changes with time. Okay? For the vast majority of applications, we're going to be dealing with constant accelerations, so we won't need to distinguish between average and instantaneous accelerations. That's not true for velocity. There's a big difference between average and instantaneous velocities. I'm saying that for most cases, our acceleration will be constant, so we can ignore the distinction between average and instantaneous. Any quantity that is constant, meaning it doesn't change with time, will have the same average and instantaneous values. Okay? For most applications, we'll be using constant accelerations so in those cases, the average acceleration would equal the instantaneous acceleration at any time. So we would only have to define one acceleration, just what the acceleration was during the entire trip. Very common example is the acceleration due to gravity, okay? There's a pull on every object near the surface of the earth due to the gravity that the earth exerts, okay? It's an invisible force, we can't see it, that pulls on every object towards the center of the earth. You are all intimately familiar with gravity, okay? You deal with it every day. If you trip, gravity is what pulls you flat on your ass, okay? If you were to take any object, no matter the size of the object, no matter the mass of the object, okay, ignoring the effects of air, if you were to drop that object, they would all accelerate downward at the exact same rate. Every object, no matter if it's a bowling ball or a bunch of feathers. You guys should look on YouTube. If you just type in BBC, bowling ball feathers, vacuum. It'll probably, as soon as you type in BBC bowling, it'd probably be like the top hit. Bowling ball and feathers in a vacuum. They actually get in a giant vacuum chamber, one that's several stories tall. They suck out all the air so there's no air resistance, hang a bowling ball and hang feathers at the top, and then drop them at the same moment in time. And you can see that they travel together the entire way down, and they land on the ground at the exact moment in time. It's because they're both accelerating at the same rate. So they both start at rest, and they're both picking up the same amount of speed every second. Because they're picking up the same amount of speed every second, they move together perfectly, and they hit the ground at the same time.
The weight has nothing to do with it.
The weight has nothing to do with it.
So if there were air, then
If there was
feathers
air,
would,
it'd be different, yeah?
Yeah, and bowling
So
balls
here,
would
let me
be different.
just show it.
Makes sense.
I might as well just show it. Because they do both. They drop it with air so that you can see what you expect, which is that the bowling ball, neither of them are good, that's too dark.
I mean, we can open the windows if we, I mean,
Nah,
the
that's
blinders.
fine. That's just like way too much effort. So in air, when there's air resistance, the air is an actual substance. Even though you can't see it, it's a physical substance that's physically there. So when an object moves through the air, it has to push the air that's currently there, it has to push it out of the way. That produces drag, which is just like friction, and drag slows an object down. Gravity is stronger than air resistance, so the object will continue falling and it will continue speeding up, but it just won't speed up as quickly. If an object's in a vacuum and it doesn't have to move any air out of the way, it'll accelerate at the fastest possible rate, just the rate that gravity pulls all objects down. But when there's air in the way and the object has to move that air out of the way, it reduces the acceleration. That acceleration depends on how large the surface area of the object is. If you have like an arrow, that arrow has a very, very small profile when you look at it. When you look at an arrow or a ruler, there's a very small cross section. So the amount of air that it has to move out of the way when it's traveling like this is very little. There's only this tiny amount of air that it has to move out of the way. But if you have like a sail, like a giant piece of fabric, that sail has a giant cross section, and you have to move a ton of air out of the way to get it to travel through. Okay, so drag has to do with the surface area. A bowling ball doesn't have that much surface area relative to its weight as compared to a feather. A feather has a ton of surface area relative to its weight, so it produces a lot of drag. Okay, right, that's in a vacuum. You get exactly what you expect. Right, the feathers take a lot longer, they have a lot of drag. Now what they've done is they've sucked out all of the air inside the vacuum chamber, and they're gonna drop them with no air resistance. Obviously this is in slow motion. So the feathers no longer get diverted out of the way. They no longer float down like this because there's no air to catch them. And they're gonna fall together, always at the same location because they're picking up speed at the exact same rate. And then they're gonna hit the ground at the exact same time. Okay, and that's what happens in a vacuum when there's no air in the way. All objects, no matter how large they are, no matter their weight, no matter anything, all objects are going to accelerate at the same rate due to gravity. Any questions about that?
So in that case, it's only gravity affecting.
Only gravity is acting on it, yeah? Because we sucked out all the air in that case. Okay? The acceleration due to gravity near the surface of the Earth the acceleration due to gravity we give by the letter G. It's about equal to 9.81 meters per second squared. That's the value most likely that Mastering Physics is going to want you to use on your homework. In class, I'll use a simplified value just to make the math in class easier. I'll just use 10. These little squiggly lines means about equal to, and I'll just use 10 meters per second squared. And remember that that number is constant. So when we're talking about an object that's just allowed to fall freely under the influence of gravity, that's going to be an example when the acceleration is constant. We're going to do a lot of problems where we assume that the acceleration is constant, because that's the simplest possible scenario that we can cover. Okay? Any questions? All right. Another feature of acceleration that I want to make clear is that acceleration has to do with velocity. Acceleration is a change in velocity. It's not necessarily the change in speed. Velocity has two features of it. It has two pieces. Velocity has a magnitude and it has a direction. Okay? There's a particular type of motion known as uniform circular motion. This is something we'll talk a lot about later on.
I'm sorry, you said the change in velocity is not the change in,
Speed. Those are two different things. Velocity is a vector. It's how fast you're going. That's the speed plus the direction you're moving in. Okay?
the speed would also be the magnitude?
Speed is just the magnitude, just how fast you're going. Velocity is both how fast you're going and the direction you're moving in.
Thank you.
Okay? Uniform circular motion. The circular is pretty obvious. It just means that as you're moving on your path, you're always the same distance from a point at the center. And the uniform means that the speed is constant along the path. Okay? So Ferris wheel is a pretty good example of an object undergoing uniform circular motion. That you just have a basket on the Ferris wheel, here would be the center, and that basket moves at a constant speed on a circular path so that it's always the same distance from the center. Okay? The Earth's motion around the sun is pretty uniform and circular. Okay, it's not quite circular, it's a slightly different shape called an ellipse, but it's almost perfectly circular. And the speed of the Earth around the sun is almost perfectly constant, so we can approximate it as being uniform circular motion. Same thing for the moon around the Earth. The motion is approximately uniform circular motion. So if we have the center here, the path, the path would be a circle around it, and at every point on this circle, if you were traveling like this, so this would be counterclockwise motion, your speed, v, would always be the same. Okay? Is an object undergoing uniform circular motion, is that object accelerating?
No.
So I got no from some people. Is an object undergoing uniform circular motion accelerating?
Yes.
Yeah.
No.
No. No, because
But
the
it's
speed is not constant anymore.
Yeah, it's uniform.
So accelerating would be picking up the speed, basically.
It would be accelerating.
See, yeah.
Acceleration does not have to do with speed necessarily, it has to do with velocity. Velocity is not just how fast you're going. The speed is constant in this problem. That object's speed is definitely changing, but that does not mean its velocity is constant. Its speed is constant, but its velocity is changing because the direction that the object is moving in is changing. The object here is moving straight up. The velocity is always tangent to the path that you're taking. The velocity here is to the left. The velocity here is down, and the velocity here is to the right. So even though the speed is the same everywhere, the speed is the same value v everywhere, the velocity is different because its direction is different. Anytime an object moves along a curve, it has to accelerate. Because a curve means your direction is changing. And if your direction is changing, your velocity is changing.
So what the value will be?
Oh, it doesn't matter what the value is.
But the value itself is gonna change?
The vector is going to change, but the speed isn't. So what if the speed was 10 meters per second? And I said that this was the x direction and this was the y direction.
So it's gonna be the same value but negative, positive?
Yeah,
Okay.
this vector would be 10 meters per second in the y direction. This vector would be negative 10 meters per second in the I direction. This would be negative 10 meters per second in the y direction, and this would be positive 10 meters per second in the x direction. And then if you had an intermediate case, if you had an object here, okay, where it was exactly halfway, then in your coordinate system, this angle would be 45 degrees. So you could break this up into an x component and a y component. The x component would be v cosine of 45. The y component would be v sine of 45. If you plug those numbers, 45 cosine times 10 is 7.07 or 7.1, let's say, then your vector v would look like negative 7.1 meters per second I hat. This is also negative minus 7.1 meters per second j hat. But no matter what vector you chose, no matter where you chose it, if you did the Pythagorean theorem on it, you'd always get an answer of 10. Its magnitude would always be 10. But the vector itself is changing because the direction is changing. Okay? Remember that velocity is a vector and it depends on direction. Okay, so you can't in your mind exclusively associate acceleration with changes in speed. Most people in everyday language, they talk about acceleration as being controlled by the foot pedals in a car. If you hit the accelerator, the gas pedal, you speed up. If you hit the brake, you slow down. But you can also accelerate your car with the steering wheel. If you turn left, even if your speedometer never changes, if your speedometer is 30 miles an hour and it stays 30 miles an hour, by turning the wheel to the left, you're changing the direction of your velocity, and so you must be accelerating. Okay? Because your velocity is changing, even if only its direction is changing.
You can also have the same direction in a different
Speed,
and that's-
absolutely. Or both could change.
Okay.
So you could be going in a straight line, and you could hit the gas pedal, and you're going faster, so you're accelerating. You could be going in a straight line and hit the brake pedal and move slower, so you're accelerating. Or you could turn and hit the accelerator, so you're changing direction and you're speeding up. All of those are examples of acceleration. Okay? If either of these features change, then the velocity necessarily changes. Okay? Any questions? Yeah.
So in general, if the velocity changes, acceleration changes?
No, in general, sorry, if velocity changes, you have an acceleration. Sorry, I misspoke here. If your velocity changes, you have an acceleration. Okay, the question was, is the object accelerating? And the answer is yes. For uniform circular motion, it turns out that the magnitude of the acceleration is always the same everywhere in here. Its direction does change, but its magnitude will always be the same. So just because your velocity changes, it does not necessarily mean that your acceleration changes. Okay? Any questions? All right, now I want to talk about how we can use these different kinematic variables to describe the motion of an object. Okay? For now, And for the vast majority of problems we come across in this class, like I said, we are going to consider motion with a constant acceleration. When we study the motion of an object at a constant acceleration, I'm going to call that the study of kinematics. This is not technically the full definition of kinematics, but this is the definition that we will use so that we'll always be able to talk about this special case when acceleration is constant. So in this class, we'll consider kinematics to be the study of motion at a constant acceleration. If the acceleration is constant, then we have a set of kinematic equations that allow us to describe the motion of an object and the different features of the object's motion at any point in time along an object's path. Okay? We are specifically talking about motion in one dimension. So for now, for this chapter, we're not going to consider objects turning. We're going to consider objects that can move forward or objects that can move backwards. Or we can do a vertical one-dimension problem. So we can consider an object going up and an object coming down. Those are both one-dimensional problems. The one-dimensional kinematic equations look like this. Okay? These three equations describe 5 variables. There's delta x, there's v naught, this is v sub 0, there's v, there's a, and there's t. These 5 variables are delta x is displacement. It's not distance, it's specifically displacement. This v with the 0 subscript is the initial velocity. By the way, we call this v naught. That's how you say this, v naught, as opposed to saying like v sub 0, which just takes longer to say. Naught is just a fancy way of saying nothing, or 0. V is the final velocity. A is the acceleration. And T is time. I want to talk about these variables before we jump in and start solving problems. But I'm going to describe these variables, we'll solve the problem, and then we'll be done for today. Okay, we'll work on more problems on Tuesday when we come back. All right. First of all, displacement, velocity, and acceleration, these are all vector quantities. And it's really important that you guys understand and remember that these guys are vectors. Okay, time is a scalar. Time doesn't have a direction. The reason why in these formulas I did not put arrows over the top of each of those vector quantities is because we're working in one dimension. In one dimension, you don't need to use vectors in terms of I hat, j hat, and k hat. You don't need to use those unit vectors to describe vector quantities. There are only 2 possible directions in one dimension. There's forward and there's backwards. So you can say that forward vectors are positive scalars, and you can say that backward vectors are negative scalars. And now you have a way to distinguish the direction of a vector. I could say that all vectors pointing up are positive, and all vectors pointing down are negative. But I'm never going to have a problem in one dimension where I have to distinguish horizontal from vertical. That's a two-dimensional problem, right? So I never need to bother with I hat or j hats or k hats. Those unit vectors are meant to distinguish different axes. In a one-dimensional problem, we don't have different axes, we only have one axis. So you don't need to distinguish. You just say, that direction's positive, that direction's negative. This direction's positive, that direction's negative. Or, this direction's negative, that direction's positive. That direction's positive, that direction's negative. The choice doesn't matter. The choice is arbitrary. Okay? But you have to bear in mind that because these quantities are vectors, the sign that you give them matters. Okay? Is acceleration positive or negative? Is displacement positive or negative? Is initial velocity positive or negative? Is final velocity positive or negative? The sign matters because ultimately these guys are vectors. Okay? The other thing is, initial velocity and final velocity. What kinds of velocities are those? Average or instantaneous?
Instantaneous.
Why instantaneous?
Because average is only one for the both.
Yeah, that's a good way to think about it, absolutely. There's one average velocity for the entire trip, but clearly I'm talking about two velocities here, so they can't be averages. Another way is to say this is the initial velocity that's defining a specific instant in time that you measure it. This velocity is measured at the start of your motion. It's the initial. Since it's defined at a specific moment in time, clearly it's an instantaneous value, it's not average. This one's the final velocity, it's also defined at a specific instant in time. So these are absolutely instantaneous quantities. What about acceleration?
Average.
Instantaneous or average?
Average is.
Average, instantaneous, it doesn't matter, they're the same. Remember, we're talking about constant acceleration. For constant acceleration, average equals instantaneous. When we're talking about a constant acceleration. If an object is falling at the start of its motion, what's its acceleration? 10. Halfway through its motion, what's its acceleration? 10. At the end of its motion, what's its acceleration? 10. If its acceleration's 10 everywhere through, what's its average acceleration?
10.
10. Okay? When you're talking about a constant value, average and instantaneous are the same. Okay? Any questions? Alright, let's do a problem. Let's see how this works. Maybe we'll do 2, and then we'll be done. The approach to solving any of these problems is always the same. Each of these equations has 4 variables in them. As long as you know 3 out of these 5, you can solve for any problem. So in the body of a problem, in the text of a problem, it'll have to give you information about 3 out of the 5 variables. Once you've gathered those 3 pieces of information, you can figure out what equations you use, and then just solve for what the problem's asking you for. And every problem's approached like that.
We have to memorize these formulas, right?
No,
Okay.
those formulas will be given to you
Okay.
on a formula sheet. So formulas, constants, like what G is, I just erased it, those you will not have to memorize.
Sounds good.
In this class, you want to memorize as little as possible. So like this rule, that kinematics only applies at constant acceleration, that rule you need to memorize. But that's one of the few things that you actually need to memorize in this class. Okay? The definitions you also have to memorize. Okay, but you want to memorize as little as possible. Besides that, you want to understand. That way, you don't have to memorize things. Like the rule that I had said over and over, that distance is always greater than or equal, to the magnitude of displacement. If you know the definition of distance, and you know the definition of displacement, and you know from geometry that a straight line is the shortest path between any 2 points, you should always be able to come up with this on your own, regardless of whether or not you have it memorized. Just from the understanding of the material. Okay? So memorization is typically not the way to go in physics. All right. Let's see. A car at rest begins accelerating at 10 meters per second squared. If the car accelerates for 3.5 seconds, A, what will be the car's speed? And B, how far will the car travel? This is a very run-of-the-mill kinematics problem. Anytime you approach a kinematics problem, I like to draw a picture. The reason why I like to draw a picture is because a kinematics problem has a starting point and an ending point, and it's really important that you understand what the starting point is and what the ending point is. You don't care about what happens prior to the starting point, and you don't care about what happens after the ending point. Okay? So this car, as far as we're concerned, it starts at rest. What happens before this is irrelevant. How does the car get to where it is right now? How is the car manufactured? What happens to all the atoms that the car is made up of before they were formed into a car? None of that is relevant. As far as we're concerned, time starts here. Then this car does stuff, and there is a final point to its motion. Okay? We're told that the final point is 3.5 seconds after the initial point. Okay? So the trip takes a time t equals 3.5 seconds. So the final point, as far as we're concerned, happens 3.5 seconds after the initial point. What does this car do 4 seconds later? We don't care. What does it do an hour later? What does it do a year later? We don't care. As far as we're concerned, time starts here and time ends here. Okay, you have a definitive start and a definitive end to every kinematics problem. And you need to understand which is the starting point, which is the ending point. Okay? Now, another reason to draw a picture is that these 4 quantities, 4 out of the 5, are vectors, and you need to know their directions. Okay? The car is moving to the right in my picture. So what's the direction of its displacement?
Right.
To the right. Okay, so positive, put that to the side. Right now, we haven't said what's positive and what's negative. But we can all agree that if the car starts here and the car ends here, its displacement's to the right. Okay? So I'll draw that displacement.
So basically, the first thing you figure out is positive or negative.
You just choose one. There's no figuring out. You choose one. It's entirely up to you, and it doesn't matter which one you choose.
In any problem?
In every problem. Every single problem. It doesn't matter. Do you guys want the left to be positive or the right to be positive? The right. There's usually a natural choice to make. The car's moving that way, so it feels natural to say that way is positive, but you will get the correct answer to the question no matter what you choose to be positive. You can choose the left to be positive, you'll still answer the question correctly. Okay? But let's just choose the natural positive. The natural positive's to the right, and in this case, delta x will be positive because it points in the positive direction. Okay, but if I chose the left to be positive, then delta x would be negative. Okay? And you could still get the correct answer even if delta x is negative.
So basically choose a side.
Yeah, just choose one and stick with it. As long as you choose one and then you're consistent, you'll get the right answer. Okay? Choose a positive, stick with it, you'll get the right answer. It doesn't matter which positive you choose. Okay? The car is initially at rest. So the car is at rest and then something happens. In a problem, information can be given explicitly. Like this 3.5 seconds, this 10 meters per second squared. You are explicitly told those numbers. Information can also be given implicitly. This problem implies that the initial velocity of the car is 0. But the problem doesn't outright tell you that the initial velocity is 0. Okay? So you have to sometimes look for those hidden bits of information. But the initial velocity, V0, is 0. The final velocity here, where's it going to point? Left or right? Right, car's moving to the right. Oh, sorry, that's V. Not A. I was thinking about acceleration in my head. Now, a rule that you guys want to know is that if you have a velocity in some direction and an acceleration points in the same direction, this object speeds up. If you have a velocity in some direction and the acceleration points in the opposite direction, this object slows down. If this car is at rest and then it starts accelerating, is it speeding up or slowing down? Speeding up. So the velocity and the acceleration have to point in the same direction.
To speed up.
Yep. To speed up, they have to point in the same direction. If the velocity is to the right, where does the acceleration point? To the right.
In this case.
Yeah. Now I know the direction of all of my vectors. These rules are really important to know. Okay, this is another thing that I would just recommend memorizing. One of the few things that I would recommend memorizing. Okay? Any case where an object speeds up, the velocity and acceleration point in the same direction. And vice versa. If velocity and acceleration point in the same direction, the object speeds up.
What about the bottom?
If the velocity and acceleration point in the opposite direction, the object slows down. So if I were to say that this car was traveling at 10 meters per second and it hits its brakes and comes to a stop, where would its velocity be pointing? To the right, because it's moving to the right. But where would its acceleration point? To the left, because any object that slows down, its acceleration and velocity point in opposite directions.
So when you brake, it looks like the wheels going back.
Not quite. That's a perspective thing.
Okay.
That's something else.
Okay.
Okay? Any other questions? These rules are important to know so that you can choose the proper direction for acceleration. Just because this object is moving to the right does not guarantee that it's accelerating to the right. It's because it's moving to the right and speeding up. Yeah.
It's just because if we if we put our foot on the brakes, it's
Yeah.
basically negative acceleration. That's why.
Exactly.
Right.
But remember, once again, the positive and negative sign is irrelevant.
Mhm.
So the concept of positive and negative, you don't want to like cling to that concept. Okay? If I have a car that's moving to the right, it has a velocity to the right, and this car is slowing down so that after it moves, it's stopped. I haven't chosen any positive and any negative direction, but I know for a fact that its acceleration points where?
Opposite direction.
Opposite, so to the left. Its acceleration has to point to the left to obey this rule. And that does not rely whatsoever on saying positive or negative. Okay? Any questions about that? All right, so we have everything here. Let's write down our 3 variables that we know, okay? Because we need to know 3 things before we can choose an equation and answer the question. What 3 numbers do we know?
Oh, we
Time.
need
Initial
the
velocity.
second
Initial velocity, v naught, is 0.
acceleration and
Time is 3.5 seconds. And acceleration, is it positive or negative 10?
Positive.
Positive, right? Sorry, here I erased it, but we chose this to be positive. It's positive 10 meters per second squared. Something, by the way, that's worth memorizing at the beginning. You're going to need to know this anyway, but it'll help you when you start solving these problems. It's worth knowing these units by heart. This is meters, meters per second, meters per second, meters per second squared, and seconds. That way you can just look at the units and you know right away that's acceleration. You look at the units and you know right away that's time. Okay? Now that we know these 3 variables, what are we looking for? Part A, what are we looking for?
First speed.
Final speed. Final velocity, technically. Which of these 3 equations, 1, 2, or 3, should we use to solve for final velocity?
Second one?
The second one. So for part A, I'll say V equals V naught plus AT. V naught is 0, so I can just cancel that. A is 10, T is 3.5, so its final velocity is 35 meters per second. Any questions about part A? Part B, what are we looking for?
How far?
Yeah, so how far? Which of these 5 variables
The
will
first
tell
one.
us the distance that it travels?
The first one,
If we, what are we looking for, what variable?
the displacement.
Displacement. Okay, displacement and distance are not the same, but this car is traveling in a straight line. So in this problem, they will be the same. Okay, that's one of the nice things about one-dimensional motion problems. In one dimension, when you're traveling in a straight line, distance and displacement are going to be the same. Okay?
The
So
variables?
for, say that again?
The variables or the answer?
The answer is how far. How far is a distance. Distance doesn't appear in any of these equations. But you know that since this car is traveling in a straight line, its distance is equal to its displacement. Okay? So you're not solving for distance, you're solving for displacement, and you're utilizing the fact that they're equal when you travel in a straight line. Okay?
Okay.
Any other questions? So we said first equation, delta x is v naught t plus 1/2 AT squared. V naught is 0, so I ignore that first term. 1/2 A is 10, T is 3.5 squared. Is 61.2. Couple of things. The number of significant figures doesn't matter when I'm working in class, doesn't matter on the exam. On the exam, you just choose whatever answer is closest. Okay, so I got 61.25 on my calculator. The possible answers on the exam wouldn't be like 61.2 and 61.25. Like I wouldn't include both of those. I'd include like 61.2 and like 75.8 and like 32.1. They'll be dramatically different. So just choose the answer that's closest. On mastering physics, it does care about significant figures, so you might need to mess around with